Alrighty, we're here to talk about frequency tables. So we have something called a two-way frequency table that gives the counts of people or objects based on two categories. So the count is like how many of them occur. And then we have a two-way relative frequency table, different thing. It displays the ratio of the total number of events for each category in a data set rather than the raw counts themselves. So if you look at these images at the bottom here, on the left is a frequency table. It shows the actual number of precincts that voted yes on some initiative, or people in a precinct that voted yes, people in precinct 2 that voted yes, precinct 1 voted no, and precinct 2 voted no, as well as the total in both precincts combined. On the right, we have the relative frequency table, which is a ratio based on the total number that were in the actual table. So here, there were 1,500 people. That's essentially the denominator. We're taking like the 495 out of 1,500. That's where 0.33 comes from. 405 out of 1,500. That's where 0.27 comes from, and so on. So we're taking the ratio of what actually happened over the total number of options, in this case, in that precinct. And in a relative frequency table, we can have a joint relative frequency, which is the ratio of the number of people or objects in a particular category relative to the total. So like I was just explaining. And then on the outside, on the edges, so the right-hand column and the bottom row, we have a marginal relative frequency, which is the sum of the joint, that should say joint relative frequencies in a row or column. So if I'm looking at precinct 1, everyone that voted yes plus everyone that voted no, 0.33 plus 0.27 gave us this 0.60. If I'm looking at column 1, precinct 1 yeses plus precinct 2 yeses, 0.33 plus 0.18 gave us this 0.15, or I'm sorry, 0.51. So in general, how are these purple and green cells created? By dividing each frequency with the total number of voters, in this case, 1,500. So what is the probability? We can use a relative frequency table to determine the probability of some event occurring. In this case, it says, what is the probability that a randomly selected voter lives in precinct 1 and supported or voted yes on the initiative? So I look at my relative frequency table and I find precinct 1 voting yes. That is the 0.33. In this case, that is an example of a joint relative frequency. What is the probability that a randomly selected voter lives in precinct 2? I don't know if they voted yes or no, but just that they live in precinct 2 in general. So that's when I'm going to look on the column on the far right. Precinct 2 leads me to 0.4. That is a marginal relative frequency because it's a sum of the people that voted yes and the people that voted no, specifically in precinct 2. What is the probability that a randomly selected voter supported the initiative, no matter where they came from, precinct 1 or 2? So I look at the first column. The bottom of the yes column is 0.51 because I added the yeses from precinct 1 and the yeses from precinct 2 and got 0.51. That's another example of a marginal relative frequency. So we're going to make our own tables here. It says a wildlife biologist captures, tags, and releases a sample of 2 species of snapping turtles as part of her research. There are 50 male and 62 female common snapping turtles, and 46 male and 42 female alligator snapping turtles. We're going to make a two-way frequency table and a two-way relative frequency table of this data. So we are going to have one section represent the gender and one section represent the species that are observed by this biologist for our frequency table. So if we look here on the left, I've got my regular frequency table. These are just the raw values. My first column, I went with male. Second column, female. The last column is going to be the total. And then my first top row is going to be the common snapping turtle. My second row is going to be the alligator snapping turtle. And then the bottom row is the total. So there were 50 male common snapping turtles and 62 female, a total of 112 common snapping turtles. There were 46 male alligator snapping turtles and 42 female, a total of 88. That means there was a total of 96 males that were observed and 104 females out of a total all of them combined of 200 snapping turtles in general, alligator and common combined. And then when I make my relative frequency table, I take each of the values and divide by 200, because in this case, that is the total number of snapping turtles. So 50 common male snapping turtles out of 200 gave me 0.25. 62 out of 200 gave me 0.31. 0.25 plus 0.31 can give me 0.56. Then for the alligator snapping turtles, 46 male out of 200 total is 0.23. 42 female out of 200 is 0.21. 0.23 plus 0.21, 0.44. And then you add up the total males and the total females to get the 0.48 and the 0.52 respectively. That's where these numbers are coming from. Keeping that same data, if we're going to find the probability, we're going to do probability still. Find the probability that a turtle that the biologist tagged meets each of these conditions. So first condition, the turtle is a male common snapping turtle. So I'm going to go to my relative frequency table. I'm going to find male. I'm going to find common. I see a 0.25. My answer there is 0.25. The second one is the turtle is female, just in general. So I need the total for females. That's going to give me 0.52. All of the females combined, 0.52. And then the last one, the turtle is an alligator snapping turtle. Doesn't say if it's male or female. So my sum for the alligator snapping turtle is 0.44. That's section 17.2. Now we're going to move on to 17.3, which is about mutually exclusive and inclusive events. So two events are said to be mutually exclusive if both events cannot occur at the same time. It's impossible. For example, if you're flipping a coin and the results you can either get heads or tails, right? You can't get both heads and tails at the same time. So getting heads and getting tails are mutually exclusive to each other, okay? So here we have a Venn diagram showing the possible outcomes for selecting a random tile out of a bag of tiles numbered 10 through 30. Event A consists of drawing a tile with an odd number. Event B is drawing a tile with a number divisible by 4. Are there any odd numbers divisible by 4? No. Are there any numbers divisible by 4 that are odd? No. So these two events are mutually exclusive. They can't happen at the same time. So looking at this Venn diagram, there is no overlap. Okay? So if you can draw a Venn diagram with no overlap, those two events are mutually exclusive. So let's make our table. We're going to have the columns represent odd versus even, and the rows, left to right, represent divisible by 4 or not divisible by 4. So looking at all of the outcomes here in our Venn diagram, it lists it for us. That's so lovely. Event A is all of the odd numbers, okay, that are not, I'm sorry, yes, all of the odd numbers. Event B is all of the numbers divisible by 4. So here we have our table. There are no odd numbers that are divisible by 4, so that's why there's this 0 here. If I look at event A and event B, there's no overlap, so I don't have any values that match both those conditions. I do have 10 numbers that are odd and not divisible by 4 because I have 11, 13, 15, 17, 19, 27, 25, 23, 21, 29. So there's 10 of those. Then if I look at the even values that are divisible by 4, there are 5 of them. 12, 16, 20, 24, 28. The even numbers that are not divisible by 4, so outside of both of these ovals, 10, 18, 30, 14, 26, 22, there are 6 of those. So I have 11 total even numbers in this data set. And then I can also find my marginal counts. 0 plus 5 is 5, 10 plus 6 is 16 on the right-hand column. My marginals for the event B, 0 plus 10 is 10, 5 plus 6 is 11, out of 21 total possibilities. So keeping that same info, I've already kind of explained this, but it says, why is there a 0 in this two-way table? There's a 0 because there aren't any numbers that are divisible by 4. Sorry, my animation's got ahead of me. Something's been spoiled, but that's okay. For the following situations, we're going to write their probability notation and find the probabilities. So let's start with B because it's already given to us. It says choosing a tile whose number is divisible by 4. So I'm looking at divisible by 4. There are 5 of those total. So I'm looking at my marginal count there. All of the ones divisible by 4, there are 5 of them, 0 plus 5, out of 21 total options, okay? Part A, going back a step, choosing an odd number tile. Again, all of the odds combined, there are 10 of those, out of 21 total options. That's another marginal. And then choosing either an odd number tile or a tile whose number is divisible by 4. So I had my odd number tile from part A. I had my number who's divisible by 4 from part B. I'm going to add those together. So I have 10 over 21 plus 5 over 21. They have the same denominator. So I just add across the top and get 15 out of 21. Now, two events are considered overlapping events if they have one or more outcomes in common. These are also sometimes called inclusive events. So you have mutually exclusive and then you have inclusive. So here we have B is fully inside of event A. If you can see that in the diagram, all of B exists completely within event A. So here, event A represents drawing an odd number, and event B represents drawing a tile with a prime number. So these are all of the prime numbers between 10 and 30. All of those are odd. The only even prime number that exists is 2. So that's definitely not between 10 and 30. So all of the rest of the prime numbers are odd. Okay, all of those exist within event A because event A just represents the odd numbers. And then outside of both of those events are all of the even numbers because none of those are prime and none of those are odd. So we can make our frequency table. I'll give you a chance to set it up. Pause if you need. Okay, now if you switch your rows and columns with what I have, that's fine. Your columns can be my rows. You could have done prime as your first column, composite as your second, and then odd as your first row, even as your second. That doesn't matter. As long as you have everything lined up, we're good. So there are 6 prime odd numbers, so everything in event B. There are 0 prime even numbers. We already talked about that. There are 4 composite odd numbers because 15 has factors besides 1 and 15. 25 has factors besides 1 and 25. 21, 27, they all have factors besides 1 and themselves. So those are your composite odds. And then the composite evens, there are 11 of those because they're all at least divisible by 2. So they're definitely composite. And then you have your marginal counts. So let's find some probabilities and write their notation. Now, once again, my animations are a little bit off. I'll fix that for next year, don't you worry. But we are going to find the probability of an odd number tile. We're choosing an odd number tile. So of all of the odd numbers, we have 10 of them. And you can look back at your frequency table and say, hey, look, odd has a total of 10. So I can do 10 out of 21. And then I'm going to skip to part C because that's what my animations did. Part C says choosing a tile whose number is both odd and prime. So that is the intersection of events A and B. It's where both of those things are occurring. So that means it's fully everything within B, essentially. Okay, so we get a total of 2 out of 7. Part B says choosing a tile whose number is prime, just prime in general. Okay, and that is, there are 6 of those out of 21. That reduces to 2 out of 7. Okay, that's where the answer for part C came from, because all of the numbers that are prime are also odd. So those are essentially asking you the same question, just in a slightly different way. And then finally, we have choosing a tile whose number is either odd or prime. So the or tells me this is an intersect situation, whereas part C was a union situation. So or, odd or prime means everything that's contained in A as well as everything that's contained in B. So all of those values we have 10 out of 7 because that's essentially the same as choosing an odd number tile. Now in general, for 2 events, we can find their probability of either one for a single trial using something called the addition rule. That says that the probability of A or B, that's your union, A or B happening, is the probability of A plus the probability of B minus their intersection. And the reason we subtract that intersection is because we don't want to double count where they overlap. Okay, so if I have, if I go back to, let's go back a couple of slides. Let's see if I can do, no, all of them were not going to overlap. Never mind. Anyway, the reason that we have that subtraction is so that we don't have to worry about an overlap being double counted. So everything that's in A plus everything that's in B, but there are some things that are in both A and B, and I just don't want to double count them. Okay, so that's why we're subtracting here. So we've got this spinner, A, B, C, D, E. and they also have their own colors. We're going to start by finding the probability that the spinner lands on blue or A. So that's the probability of blue plus the probability of A. But in this case, I also have a blue A. So that is my overlap. So here I've got 2 that are blue, A and C are both blue, out of 5 total. I have 1 A out of 5 total, and I have an overlap of a blue A. So I'm going to subtract 1 out of 5. So this probability ends up just being 2 out of 5. Then it says determine the probability that it lands on blue or D. So for blue, again, I have 2 out of 5. For landing on D, I have 1 out of 5. And then the overlap, well, the D is actually red. So in this case, there is no overlap. That's a 0 out of 5. So adding 2 out of 5 plus 1 out of 5 gives me 3 out of 5. Once again, let me know if you have questions.